Dear students, in this lecture, I'll be dealing with three important concepts. One is the notion of distance in connected graphs. The second definition is that of bipartite graphs. And the third one is complete bipartite graphs. Already you have learnt what are connected graphs and some of the special classes of graphs like complete graphs, then cycle, path, etc. Bipartite graphs are also very important in graph theory. Let us see how we can define distance between two vertices in a connected graph. Distance between two vertices in a connected graph is defined as follows. Let G be a connected graph and you have u comma v as vertices of G. So u comma v belongs to v of G. Distance d of u comma v from u to v is the length of the shortest uv path. Once again, distance is not the edge. There need not be an edge between u and v, but as the graph is connected, always there will be a path. But we require not the length of all the paths, but the length of a shortest uv path. There may be more than one shortest path. Let us see an example and you will understand it. For example, if I have a graph like this, let me call it as a graph with vertex at u, v, w, x. So there are 4 vertices and 5 edges. What is the distance between u and w? So I can travel from here along u to v and w. That's the shortest path. I can also move from u to x and x to v. Length is 2, here also length is 2. There is another path. There is another path, u to x, then here, then here. That is not a short path because length is 3. So there are 2 paths, u, then I can move to v, I can reach w. So that is a u-w path. Similarly, I can u to x and w. That's also a shortest path. So anyhow, length is 2. One edge here, one edge here. So duw here is 2. Now what about distance between u and x? That's 1. Straight away the edge. If there is an edge, distance is always 1. Now what is the distance between v and x? That's also 1. So only there are 2 vertices, namely u and w, having distance w. Other vertices have distance 1 between them. Okay. So now duv is a metric. Metric means the following conditions should hold. Usually all the distance functions are metric functions. We'll learn about the metric topology in the next semester. Anyhow, just for the your preliminary understanding, you clearly understand that duv, some kind of distance, is a metric if it is non-negative. Every distance is non-negative. Will not be having a negative distance. 0 or non-negative, that is 0 is, then distance between 2 vertices is equal to 0 if and only if u equal to v. If u and v are the same, if the vertex u is same as the vertex v, then distance between them is 0 because we will be having a path of length 0. Then symmetry must be there. d of uv must be equal to distance from u to v must be same as distance from v to u. If there is a uv path, remember there will be always a du path also. Therefore it is symmetry. Then this one is what we call as a triangle inequality. Distance between u and v must be less than or equal to distance between u and w plus distance between w and v for all u, v, w. So the last one is called triangle inequality. So once again, these 4 conditions hold good for any distance metric. That is true in the case of graph distance also. In a connected graph, this will be a metric that you can check. So anyhow comes a very important definition, bipartite graphs. A graph G is said to be a bipartite graph if the vertex at V of G can be partitioned. Partition means V of G, it can be written as X union Y with X intersection Y as phi. There is no common element between X and Y. X contains certain vertices and Y contains certain vertices. Then there is no common vertex to both of them. So the vertex set can be partitioned into X and Y such that every edge of the graph, E belongs to E of G, has one end vertex in X and the other end vertex, end in Y. So let's have an example. This is a bipartite graph, Y. So this, so let me take this as U, V, W, X. So this is actually, I told you there are 4 vertices, and therefore it is a C4, cycle C4. So cycle C4 is bipartite because, see, let us have a look. Let us have a look at the graph once again. U has this n vertex here. Then I have to keep this in Y. Then X is there in if I keep this like this, so let me have it like this. Okay. U and V. So let me take X like this and Y like this. Let me keep U here. Then I should keep V on the other side because there is an edge connecting U and V. Then I should keep W here because there is an edge connecting V and W. Okay. Now I should keep X on the other side. U is there. Okay. This is there. This is also there. So your graph is now this one. This one. So let me cancel out this set. It will look like this. Let me cancel all the pages. So this will look like this actually. The U, then V, okay, then W, X. This is a graph, C4. C4 written, drawn like a bipartite graph like this. Therefore, this will form one set, and this will form another set. Therefore, this is X and this is Y. X and Y are called partite sets for V. And generally, if we have a bipartite graph, it is denoted by G of X, Y. Graph G with partite sets X and Y is denoted by bipartite graph is G of X, Y. Now, complete bipartite graphs, last one. A bipartite graph G of X, Y is said to be complete bipartite graph if every vertex in X is adjacent with every vertex of Y. So previously, see here, this is actually, okay, this is a complete bipartite graph. Let me give you one more example, then you will be understanding. So before that, let me have a notation. If the first partite set has m vertices and second partite set has n elements, then the complete bipartite graph will be denoted by Kmn. And order of Kmn means number of vertices in Kmn will be m plus n, and size on the number of edges will be m into n. So let's have an example. See here, let me take 3 vertices here and 2 vertices here. This is my X and this is my Y. If I want to call this as complete bipartite graph, there are 3 vertices here, there are 2 vertices here. Then I have to write it as K32. Generally, Kmn means the set X should contain m elements, m vertices, and set Y should contain n elements. So this is K32. So this must be adjacent to this one. This also must be adjacent to this one. The second vertex must be adjacent to the first of y, and here, then this is K32, K32. Okay, so K33. Now one more example if I want to explain. So here it is 3, here also this is 3. So this will become K33. This is K33. So this one is X, this one is Y. Okay, that completes today's discussion, and we'll have the characterization of bipartite graphs, which is a lengthy theorem, in the next video. Okay, thank you so much for watching.